Hello everyone, welcome to Unacademy. So my name is Jagriti Sharma and this is my YouTube channel, and I'm an educator on the Unacademy Plus platform, guys. And my ranks or the CSIR NET exam are All India Rank 24 in December 2018, All India Rank 11 in June 2018, and All India Rank 27 in December 2017. So basically I have qualified the CSIR UGC NET exam thrice, and I'm making these videos. Specifically, I'm going to talk about IR spectroscopy, instrumentation, and sample handling today. Okay, and I think that the video will be beneficial for the B.Sc and M.Sc students, the CSIR UGC NET Aspirants, the GATE Chemistry Aspirants, TIFR and BARC Aspirants as well. Okay, so let's start the video. So yes, as I have told you, my name is Jagriti Sharma and I am an educator on the Unacademy Plus platform as well. So guys, in the Plus platform, you get all the live and structured courses. So basically, like in a coaching center or like in a usual class, we are having complete 6-month courses, right? So if you are starting from now, your preparation for June 2020. Alright, so we are going to start our courses from January for the preparation of June 2020 CSIR examination. Alright, and we will be having a daily class, or let's say a very structured class system in which all of your syllabus will be covered, and along with that a lot of previous year question solving along with a lot of practice question solving is also going to take place. You're also going to have doubt session over there. Right, so there is a doubt session after every 3 classes, and also there are weekly quizzes in the Plus platform. Alright guys, so this is all a combination on the Plus platform, Unacademy Plus. Alright, and to give you a feel of how the Plus works, basically you can come and take part into the special classes. So what are special classes? They are live classes, but they are free for everyone to watch. Right, and these are 1-hour live sessions basically, so that they give you a feel of how the Plus works. Okay, right, and if you want, then you can just visit my profile and you can watch the free video courses that I have made. You can also watch all the live session, because in the live classes I have tried to solve maximum previous year question on the CSIR exam. And guys, and after watching my content, if you want to subscribe for the Plus version, because the Plus platform is a paid platform. All right, so if you want to subscribe for the Plus platform, then you can use my code Jagriti S. Okay, and this code is going to give you a 10% discount in whichever package you select. There are 1-month package, there's a 3-month package, 6-month, 12-month, as well as 24-month package as well. Okay, so my code is going to fetch you a 10% discount on whichever package you want to subscribe to. And there is one more thing that I want to share with you, that there are many other educators, many other top educators like me on the platform. So if you are using my code for the subscription, so you are going to get everything under the CSIR category. You can get all the subjects. You are going to be able to access the content from all the top educators. Alright guys, so this was about the Unacademy Plus platform. It is a really good platform and a lot of content is available. First you can watch it free, and if you like it, you can move on to the paid package subscriptions. Alright, so today we are going to talk about the IR spectroscopy. First of all, let us understand what is the spectrum basically. So guys, you must have seen this image in a lot of books, right? So what happens over here is, we are just going to understand that which region we are going to talk about in the IR spectroscopy. Okay, so first of all, we are having X-ray, which is very high in energy, because over here, if we are going from right to left, the energy is increasing and the wavelength, it is decreasing. So it is having a short wavelength, so wavelength is decreasing and energy is increasing, isn't it? See guys, we know we have this formula, E is equals to hc by lambda. So we know that if the lambda increases, energy decreases, and vice versa. So if the lambda is decreasing over here, then the energy is definitely increasing. So the X-ray is going to have the highest energy value, then comes ultraviolet region, then comes the visible region. Okay, so this region over here is our UV visible region, and I have also made a video course on the UV visible spectroscopy, guys, so you can just visit my profile in the Unacademy channel also, and you will be able to see that I have made a special course for the ultraviolet spectroscopy, and there are also previous year questions in that course. Okay, so today we are going to talk about the vibrational infrared region. Okay, so this is our vibrational infrared region, and it expands from 2.5 micrometer to 15 micrometer. Okay, so so basically if you see in the spectrum, it is written like this: 2.5 micrometer to 15 micrometer. All right, but whenever we are plotting a graph, right, so basically we are studying the molecules, we are studying the vibrational spectrum of the molecule basically. So we are not going to use such this micrometer is basically 10⁻⁻⁶ meter, and we are not going to use this unit. What we are going to do is we are just going to simplify it. How? We are just going to take the wave number, right? So we are just going to take the wave number, which is represented by nu bar, and this is equals to 1 upon lambda. So it is just the opposite of lambda, as you can see. Okay, so if lambda was in centimeter or meter, then nu bar is going to become centimeter inverse. Okay, so what we have just done is we have converted our 2.5 micrometer to centimeter, and it is equals to 4000. Isn't that a better letter to write, because it is much more simpler, the unit has become much more simpler. Also 15 micrometer is equals to 667 centimeter inverse. So guys, when we are studying about infrared spectroscopy, we are going to have to remember both these things, that it can be 2.5 micrometer to 15 micrometer. It also can be written like this: 4000 to 667 centimeter inverse. Okay, then comes the infrared region, microwave region, radio frequency, and so on. So basically this region of radio frequency is very important for the nuclear magnetic resonance, basically the NMR spectroscopy, right? So for now we are only going to focus on vibrational infrared, that is why we are going to stick to this region over here. Okay, so the region from 4000 to 667 centimeter inverse is of specific interest to organic chemists. Why? Because the organic molecules give a vibrational spectrum in this region. All right, so now we are going to look at the instrumentation basically. So guys, this is a very simple representation. Okay, it is a very simple representation of the instrumentation, right? Just a 2D diagram. So let's understand this diagram. So first of all, it is our double beam IR spectrometer. Okay, it is a double beam IR spectrophotometer. All right, so the first thing that we need to talk about is the radiation source. Okay, so first of all we need to talk about the radiation source. Even some section B questions are asked. The 2 marks question can be asked that what is the radiation source used for the IR spectroscopy. Then we can say that when we are heating the Nernst filament, which is made of oxides of zirconium, thorium, and cerium. So basically we are having oxides of zirconium, thorium, and cerium, and if we are heating those oxides, or let's say we are also having one more source, which is popularly known as glow bar, right? It is popularly known as glow bar. It is basically silicon carbide. Okay, so if you are heating the filament made from these elements, it is called the Nernst filament, to 1000 or 1800 degrees centigrade, then the filament is going to release IR radiations of increasing wavelength. Increasing wavelength means decreasing energy. All right, so a variation of energy is also going to take place. So let's say if it is starting from 4000, then it is going to 667 centimeter inverse, which means the energy is decreasing. All right, so it is going to release IR radiation. So guys, basically the infrared radiations are having a heating effect. As we all know, the infrared radiations are having a heating effect. All right, so we are going to talk about that when we talk about the detector. Okay, so now we are going to talk about the beam divider, the next step. So what a beam divider does is it divides the radiation which is coming out of the radiation source equally for a reference cell as well as for our sample to absorb. So the beam divider is actually dividing the beam into two equal intensities basically. So it is dividing it into two equal intensity beams for the sample to absorb as well as for the reference cell. So what is the use of the reference cell? So basically guys, the reference cell and the sample cell, both of them are made of KCl, KBr, NaCl, NABr. As you know, why are they made of these elements? The sample cell, you know, we have popularly heard about it, that they are made of, you know, potassium chloride, potassium bromide, sodium chloride, sodium bromide. Why not glass or quartz? Because glass and quartz are strongly able to absorb in the IR region, and that is why if they are absorbing in the IR region, they would definitely interfere with the IR spectrum that we are having over here. Yes, so we don't want that. We don't want our sample container chemical to, you know, interfere. We want minimum interference in the spectrum. That is why we are taking potassium chloride, or you know, basically these ionic salts we are taking as the sample cell. Okay, then we are having two more things over here. One is the attenuator and the other is the comb. So what is their use? Basically the use of the attenuator and the comb is they have photometers. So the photometers are helping in balancing the waves before combination. So basically what happens is we are taking the you know, signal from the reference and the sample cell, and we are combining it back into the monochromator. All right, so we are combining it back into the monochromator. So the work of attenuator and the comb is to balance this you know, is to balance the signal, all right, before the combination. Alright, then we are having the monochromator, which is basically used to combine both the signals over here, and it is going to give us a monochromatic light wave basically. And the work of a detector, guys, is to detect the infrared radiation which has come out of the sample and reference cell. Okay, so basically the infrared radiation must be absorbed. Some of it is absorbed by the sample, isn't it? So the transmitted radiation is detected by the detector. And what does the detector do? So basically a detector is a thermocouple. It is a thermocouple, so it gets the signal, it gets the IR signal by heating up, because whenever IR infrared radiation are falling on a thermocouple, then the thermocouple is going to get heated, the temperature is going to increase, and that is how our IR signal is detected. Okay, and then it is passed from an amplifier, which is where it is amplified, and finally it is recorded in the recorder. Okay, so this is what we are getting. This is our IR spectrum. So guys, we also, yeah, so I just forgot to tell you, the monochromator has gratings which disperses different frequencies to be detected by the detector. So basically the work of a monochromator is to disperse the radiation, right, and only give a monochromatic beam to be, you know, very quickly detected by the detector. Alright guys, so now we are also going to talk a bit more about the recorder. So definitely we understand that the recorder is going to you know, record the signal, and it is going to give us a spectrum, but the spectrum can be of two types. In the spectrum we can you know, draw the spectrum like this: absorption versus the frequency in wave number. So basically if we are drawing it like this, then we are going to get a peak, on the signal that we are having basically, or let's say the you know, vibrational signal that we are going to detect. It is going to come like a upward peak if we are plotting absorption against the wave number. Okay, but if we are plotting transmission against the wave number, then we are going to get a dip like this. So this is our dip over here, and this is our peak over here. All right, so see guys, the thing is that the graph can be plotted either way, but the peaks will remain at the same value, isn't it? The peak is going to remain at the same value even if it is a peak or if it is a dip, because this is the characteristic transition, which is vibrational transition, which is taking place within a molecule. So if we are plotting absorption, then it is going to say that the intensity which is absorbed by the molecule is plotted, and if we are plotting transmission, then the intensity of the light which is transmitted, basically, that we are plotting. Okay, so what is the relationship between transmittance and intensity which is absorbed? It is this over here. Transmittance is equals to intensity of the falling radiation, or basically the incident light intensity, the absorbed intensity, divided by I naught. So this over here is our incident light intensity. Okay, so percentage transmittance is also can be written like this. Percentage transmittance is equals to I by I naught into 100%. Okay, and definitely guys, the light which is absorbed is going to be equal to minus log T. So this is the relationship between absorbance and transmittance. A is equals to minus log T. And see, there are numericals of various types. So basically, when the transmittance is given in some particular value, then you can use this formula. Let's say the transmittance is given 50, then you can use this formula. But if the transmittance is given in percentage, then you can easily use this formula, A minus 2 log T. Okay, and how does that come? Because whenever we are having transmittance in in percentage, then we are just going to write A is equals to minus log, let's say I'm writing 50 divided by 100. Okay, so now this 100 is going to become, minus log 50 minus log 100. Basically it is going to become plus because there was a minus over here. So log 100, as we know, is going to become 2 because it is 10 to the power 2, alright. So it is going to become 2 minus log 50. So if you don't want to do this calculation, you can directly use this formula. A is equals to 2 minus log percentage of T, okay, for doing such numericals. So these are 4 different formulas that we are having. Transmittance is equals to I by I naught, and absorbance is equals to minus log T. Also we can write absorbance equals to 2 minus log percentage of T, alright. So these are the formulas. Now we are going to move forward to see that what is the technique of sample handling, guys. It is also very important in the beginning of studying the chapter to know that how are the samples being handled. So basically, if we are having liquid samples, okay, so if you are having liquid samples, then either we can take pure liquid, or it is also called neat liquid drop, and it is added between 2 NaCl plates to form a very thin film. So as you can imagine already that we talked about why we are taking NaCl, why not glass or quartz, because in the glass or quartz are going to absorb in the IR region. Okay, so that is why we are taking NaCl over here. Alright, so NaCl plates will be there, and we just have to form a very thin film, and it can be done by adding only a drop or two of the pure liquid. Alright, the liquid should be free of water over here, because again we will get a peak for water. Okay, and there may be some changes also, there may be some chemical changes in the presence of water, so we have to take care that water is not present. Okay, alright, then if we are handling solutions, it can be solution, then what is the best thing to do? 1 to 5% solutions into NaCl cells made of 0.1 to 1 millimeter thickness. So again we are going to put our 1 to 5% of solutions into the NaCl cell, basically, okay, which is made of 0 to 1 to 1 millimeter thickness. So let's say we are having a cuvette, so we are just going to put some of the solution into the NaCl cuvette. Okay, so the solutions, again, for best interpretation, different solvents may be tried except water. So we are always going to take care that water must not be added. okay, in the solutions also. So we can try solutions of organic compound in different solvents, like they can be hexane, they can be acetonitrile, and some other solvents like ethanol and so on, right? So we can try our organic solvents as well. And if you are having solid sample, then the solid sample can be added like this. First of all, they can be made into moles. What are moles? Basically 2 to 5 milligram of solid. So our solid sample, it is mixed with nujol and pressed between NaCl plates. So guys, nujol is a hydrocarbon which does not absorb into the range that we are having, and it is very popularly used as a mole, and that is why the moles are also called nujol moles. Okay, they are also called nujol moles. And the nujol mole is basically prepared and pressed between the NaCl plates again for our IR spectrum, right? And the other possibility is 0.5 or 1 milligram of solid sample is mixed with 100 milligram of KBr and pressed into to form pellets. So basically here the solid itself is formed into pellets, all right, and these pellets are directly put into the container, right, for the IR radiation to pass through it. So here we are not taking any other container or NaCl plates. It is because the solid itself is pressed into form pellets, all right. So this is how we handle the solid sample as well. Okay, so guys, now we are going to start a bit about studying that what are the vibrations. So in this video I'm just going to tell you the modes of vibration of molecules. Okay, so what are the vibrations? So basically we are having stretching vibration and bending vibration. Okay, so guys, the stretching vibrations usually occur into the region 4000 to let's say 1200 centimeter inverse. So I'm just writing roughly basically. So into the left part of the spectrum, we are going to see the stretching vibrations, and that is the most easily interpreted one. But the bending vibrations are going to be mostly seen around 1000 to 667, or basically it can be our 1500 centimeter to 667, and this range is, guys, this is specific for bending vibrations, and it is also called the fingerprint region. Okay, and it is on the right side of the spectrum. Okay, so in the other next videos we are also going to see original spectrum, and we are going to learn how to interpret the spectrum as well. Okay, so our stretching vibrations are like this. So if we are having symmetric stretching over here, so this is carbon hydrogen bond. So if they are going to do the symmetric stretching, then both the hydrogens are going to pull on the opposite sides like this. So both are going to pull on the opposite sides at the same time. Okay, so these are our symmetric stretching. For carbon hydrogen, the symmetric stretching value is approximately around 2853 centimeter inverse. Okay, talking about the sp3 carbon basically. Now if we are doing the anti-symmetric stretch, then one of the carbon hydrogen bond is going to elongate. This bond has elongated, alright, while this bond over here, this carbon hydrogen bond, this one has compressed. Okay, so this is how the anti-symmetric stretching works, and it is around 2926 centimeter inverse. So as you can see, guys, the anti-symmetric stretching is at a greater wave number as compared to symmetric stretch, which means that anti-symmetric stretch has a higher energy. It has a higher energy, alright. Also we are going to see the bending vibration. So in the bending vibration we are having a lot of variations. Scissoring, which is working like a scissor. So if we are having a scissor like this, so a scissor basically comes over here, both the ends come together and they go back together. Alright, so this is our scissoring vibration, which comes under bending vibration at 1450 centimeter inverse for the carbon hydrogen bending. For rocking it is like this. Both of the hydrogens are moving together. Okay, so it is like rocking. Okay, so this is present at 720 centimeter inverse. For wagging, what happens is just like we usually say that how a dog is wagging its tail. That is why it is called wagging, because both the hydrogens are going to just swap here and there and here and there, basically just like a dog is wagging its tail. Okay, so this is our out of plane wagging vibration. So whenever you are going to see OOP, this is our out of plane bending vibration, and that is definitely wagging. Alright, and it is around 1250 centimeter inverse. Then we are having twisting vibrations. If it is this hydrogen is going inside the plane, this hydrogen is coming outside the plane. So guys, we know what is twisting. Yes, so this is also our out of plane vibration. OOP is out of plane bending vibration. So twisting will be around 2050 centimeter inverse. Alright guys, so what we have to do is, we don't have to remember all these values exactly, but we have to have an idea that what are our out of plane bending vibrations and what are the in plane bending vibrations. Okay, that is what we need to remember. Okay everyone, so I hope that you like this session, and if you liked it, then please like, and please also subscribe to my channel for regular updates and for more upcoming videos. Alright, for more upcoming videos and for getting regular updates on everything, and also share it to your friends if you liked it. And guys, let me also remind you that you can search for my name Jagriti Sharma on the Unacademy Plus platform, and you are going to get a lot of free content, okay, over there as well. All the previous year question, lot of previous year questions are also solved. And after watching that content, if you want to subscribe, then you can use my code, which is Jagriti S. Very simple, J capital S capital, just my name Jagriti S. Okay, thank you so much guys for watching this video. I'll see you with the next video very soon. Thank you.